My warmest greetings to participants of today's webinar. And today we continue the series of the lectures of International Scientific and Methodological Center of Ural Federal University. And today the general topic of the presentation and our speaker would be the smart energy systems. And we will speak about how smart energy systems provide revolution and provide mutual interconnection and interaction between information systems and power industry. And we'll learn some real existing European cases on how this could be implemented. And it's my great pleasure to introduce you to today's speaker. It is the Associate Professor of Grenoble Polytechnic Institute, the researcher of Grenoble Polytechnic Institute Laboratory, Raphael, Caire, and the floor is yours. Thank you very much for providing such an opportunity for us and for our listeners.
Okay, thanks a lot, Stan. Thanks a lot for the invitation and this opportunity for me to share with you some thought about critical infrastructure, how to protect them, and the place of ICT system in smart energy systems, in what we call system of systems. And this lecture is about how to understand better the different interdependencies that exist between the different systems, how to model them, and how to make sure that we can in the future enhance the resiliency of such systems. So it's mainly based on some thoughts and results from the thesis of José Libardo Sanchez Torres. You can have the link to the PhD thesis that is in English and on the French repository of the PhD. So let's jump first to the lecturer. Stan already introduced me. So I'm a PhD. I'm an associate professor in Grenoble INP, that is now the Institute of Engineering and Management of the University Grenoble Alpes in France. And I did start my career in electrical engineering in power electronic and electric mobility 20 years ago. Then I did a PhD with EDF on the, let's say, renewable and distributed generation. And I did work with EDF for several years, both in Germany and in France. And I jumped to Grenoble INP a few years ago, more than 15 years ago, in fact. So what I would like to push toward the audience today is, you should be able at the end to, let's say, at first categorize the various interdependency families for infrastructures. You should be able to recommend modeling methods at the end. And as it will be the focus on this presentation, as a highlight, describing the complex network theory to support the use of Hermitian matrix, and list the different added value of complex network theory applied to coupled infrastructures. And let's, maybe before the agenda of the presentation, let's jump first on the context. And let's go back to 2003. I think it was one of the very first events that at that level of gravity impact power system world and connection between ICT and ICT failure that is leading to a very large blackout. So we need to go back in 2003 in the blackout that happened between US and Canada. During that year, there was many other blackouts all around the world, but this one affects 50 million of customers. And that's from this blackout that we know that more or less 1 day of blackout cost 1% of GDP for a country. And what happened, in fact, is that the alarm system failed. The state estimator went to a bug, and there was, of course, in parallel line faults, as every day any power system is experiencing. But this time, the operator was not able to understand what was going on, just because he was completely blinded. And if we look at what happened the night before, in fact, so this is a night view of United States and Canada. And in fact, if we just go, sorry, let's maybe go the day after. So the day after, still Toronto, Detroit, Cleveland, Buffalo, Columbus, all this area and even Long Island are still in the dark, and it was really catastrophic for many parts. So this is from then that we knew, of course we knew it before, but we just learned how it can be critical, that power systems are now highly independent on information and communication technologies. And so if you want to be able to protect critical infrastructures, you need to enhance, of course, smart energy system at large, and we'll try to do the focus on smart cities to go further in smart energy systems, but how to enhance the resiliency of smart energy system. Well, you need at first to build knowledge on the failure trajectories of COBOL system. What does it mean? It means that you have different systems interacting one to another. And when one is failing, of course, it is having its own trajectory that impact the trajectory of other infrastructures. And so the second point you need to do is to understand, and this will be part of my presentation today, that it exists some topological interdependency. There are some links between the different infrastructure that we need to study and to understand. And at the end, when you know exactly what are the interdependencies, you're able to secure this smart energy system or this system of systems. So the basic example we can see here, power system is supplying power to both communication infrastructure and as well as the operating center. And communication infrastructure allow exchange data between the different parts. So this is typically an interdependent system. So let's discuss about the interdependencies. Of course, classically, people really focus on physical and cyber interdependencies. And as Barabasi is saying, this is a big pop of what I will present later. In fact, it exists many links between everything, and usually more than just physical and cyber links. You need to add, for instance, geographic interdependencies. Of course, when you have a common mode failure, for instance, you have a power system, a primary substation that is going into a fire, you will lose both electricity services, but as well communication services. And so geographic interdependencies are important. Logical interdependencies are very important as well. And social interdependencies are important. And more than just these types of interdependency, you need to understand what are the failures that can go from one to another. So typically, usually we say, okay, cascading failure is one of the most typical. Cascading means, for instance, you have one failure in one infrastructure that will lead to a failure in one other. You can have as well escalating. That means that you have one failure that is at the end leading to a higher impact in another one. And the third one, so escalating, for instance, is what happened as well in 2003 in Italy. There was a blackout. And in fact, because of the power system was out, most of the mobile antenna well, their supply was depleted, not enough battery in it. And when the power system wanted to re-energize his own network, he was not able to rely on this mobile infrastructure to send the order to close or open different switches. So it's typically escalating type of failure. And last one is common mode. I already discussed about the loss of a primary substation. So the outline of my presentation today, I will go through some definitions, and then I will focus on complex network modeling, and I will explain you why I need to jump into Hermitian matrices, spectral centrality, and the different algorithm we did imply. And I will highlight some point on a test system and giving you a few results before the conclusion. So let's start with the introduction and the link with smart cities. So critical infrastructure, of course, all the different governments are having their own definition. But let me focus on the one from EU that is trying to put together all the different infrastructure that if they were at any point impacted by any threats, it will harm the society in general. It's what we call critical infrastructure. So, of course, obvious one, and the one we all have in mind because of the field we are covering, is typically energy, of course, and networks. Second one, clearly, is ICT, because of more and more services we are requesting to be able to coordinate the different energy infrastructure, but not only. Financial, banking, of course, health, food, water, transportation, any type of, let's say, manufacturing, production, storage of everything that is dangerous, and of course, last but not least, government. If we focus on a smart city inside, in a classical city, you will find the most critical ones that are typically energy, ICT, health, food, water, transportation, and government. We are trying to have less impact at the level of a city because of the banking system and transport of dangerous goods. We are trying to avoid all this. And what are the typical link we can find? And maybe I can use this quite old picture, but still interesting. That is about the fact that we are in a complex, interconnected world. And let me just zoom in, not too much, just to give you some understanding. So, quite in the middle, there is electric power system. I hope colleagues from ICT won't be affected about that. The one that is in the middle is not the more important, but it's just a choice. So electric power system is of course providing power for compressor for natural gas, is providing signaling for transportation, is providing all the red arrows, so for oil, for water, and for even supplying communication infrastructure. And in fact, as vice versa, in fact, you have a lot of services offered by other different infrastructure. So for instance, communication is providing SCADA communication, so the ability for an operator to manage a given infrastructure remotely. So that's typically what we have in a power system. Maybe before jumping to the next part, I will try to make some breaks in the presentation. 1 hour is long, so we will do some little quiz, and I'm currently asking you to go on the website. So using Socrative, you can just Google it, socrative.com, and I'm asking you to log as student. So please do it. I can give you 20 seconds for that. So you don't have to use exactly this very specific link. You can just Google Socrative. You log as a student. You will have just to enter your name, a nickname, and log in the room. So maybe let me do it in parallel with you. Socrative, student. So you log on Socrative, you put your name. Sorry. The name of the room I want you to use is Caire, C-A-I-R-E, 1243. Be careful, it's 1243. And this is where you can enter your name. And from here, I'm initiating indeed a survey, and I'm asking you to think about what are the most important infrastructure in a smart city. I present you some of them, of course, but maybe you can add, you can change, and it will allow me to do a kind of survey about how different researchers are responding to the issue of, let's say, critical infrastructures in smart cities. So I can see now that we have few people already connected. And there are no good or bad answer. Okay, don't be afraid about that. Just feel what you want inside. It's just a survey to understand exactly how you are reacting to this specific field that is critical infrastructure protection related to smart energy systems. I'm giving you a few minutes. And in parallel, if some of you have any questions about my brief introduction I did so far, don't hesitate. So I know that Socrative is not the best tool to interact synchronously, but is interesting just because you can fill with plain text an answer to some questions. So you don't have to restrict to some specific multiple choice answers. And that's where it is interesting for me for the second question. So I fully agree with Stan that recycling is very important, more especially when we are in a sustainable world. I fully agree with you, Stan. Okay, maybe you can do it asynchronously, and I will just go back to my presentation, and you will have time to do it till the next break we will do. So just have to answer to the plain text. I will not answer myself. So indeed, the question, so specificity of smart cities, and what are the infrastructure that, from your own point of view, is missing in a smart city versus the first question. So I'm discussing about smart city, but maybe we need to define what is a smart city. So smart city, it's a complex smart energy system. And we are using the smart city wording to define what ICT, information and communication technology, can offer as services to improve the efficiency of city operation and the citizen quality of life. And very often people are pushing as well the local economy. So that means that we are starting from the point that ICT is adding a new complexity to cities that are becoming smart cities. And we want to focus on new vulnerabilities that emerge from the interdependency among infrastructures. So the question is how to model interdependencies among infrastructures. And being clear and honest, there is a clear lack of methods. The one we did explore a few years ago are the following. We explore complex networks. I will focus mostly here on this one. You can play as well with agent-based modeling, multi-agent infrastructure. There are some Markov possibility to model things. You have combined simulators. We did work and play a little bit with some of them. Usually it's not that easy. At that time, it was not easy to interconnect the different pieces of software together. Now it's a little bit more easy thanks to some standards to communicate between pieces of software. You can use as well Petri networks and Bayesian networks. So all of them are having some good points and some drawbacks. So let me focus on complex network theory and defining it as well. Why I'm focusing on this one is because what I said before, everything is connected. And in fact, starting from a topological approach is interesting. And so what is complex networks? Complex networks is an evolution of the graph theory. All of you know graph theory that is starting from Leonard Euler, when he had to solve the problem of Königsberg bridges. Is he able to go from every part of the city going through one bridge only? And in fact, he built a mathematical theory around it just to prove that it was impossible. And this is what we did use till 1960 with random graph theory, and somehow we had a lack of interest in graph theory just because the problem were becoming larger and larger, and we didn't have the let's say the computation ability to solve them. And so in parallel, we need to add a new field that is computer. And thanks to the big database, the processing power that was increasing more and more, in fact, complex network theory appears in the late 90s with small world networks and scale-free networks. And this complex network theory was really helpful for instance, to study typically social medias and pandemic situation. A little bit more about what are the different definitions. So what is a network? A network is referred by any system that can be described by graphs, node arcs. A graph is used whenever you want to discuss about mathematical properties. You can use a graph spanning tree to describe distribution network. And this is really a very strong tool to model the fact that you want to have every time a radial network versus something that will be more looped or meshed as for transmission system. And what we call graph theory is all the principles and theorems that are around graph and help you to solve things. Complex network is the field that describes the networks, where whenever the infrastructure is irregular, complex, and dynamic, but still relying on graph theory. And usually what we use as properties, we are using adjacency matrix, node degree, and centrality indexes, such as betweenness centrality and so on. I will present betweenness centrality, one of the results at the end of this presentation. So adjacency matrix, you all know what it is. It is saying that I'm representing the graph with a matrix-based representation, who is connected with who. What is a node degree? A node degree is how many neighbors or feed in, feed out, if it's a direct graph you have in a network. So it is qualifying the role and prestige of nodes. And betweenness centrality is something that is very used in ICT network, just because ICT systems have this dynamic behavior that is trying to self-optimize themselves and reduce the latency between the different users. And so betweenness centrality is relying on the shortest path that are going through the different nodes. And that is helping people to identify the bottleneck in the graph. So just to finalize this introduction, so please remember that a smart city is composed of various networks, including various physics. When I'm discussing about gas, recycling, water, electricity, I'm not using the same mathematical representation at the same time scale. But anyway, all of them are interacting, more or less, depending on the level of interaction, with different dynamics. It is very important to be able to be ready to use topological approach to analyze the most critical nodes to be secured. So either you have this approach that is what are the most critical nodes, or you can go as well in another way of thinking that is where do I have the weakest links, so that it could split different infrastructures into pieces. And this is where, when we think about topological approach, we put a little bit aside dynamic. Complex network theory is very promising. So let me jump into the theoretical part of this lecture and discussing about complex network modeling. So I will go first into Hermitian matrix need, spectral centrality, and different algorithm we did implement. So what we are proposing, we are willing to use a spectral centrality, a spectral analysis. What is a spectral analysis? You do a eigenvector analysis, eigenvalue and eigenvectors, that will allow you to find where are the most important nodes. And the problem is that when you want to represent different infrastructures with different physics together, either you use just topological approach, that is, I'm connected, but you will see further, we wanted to be able to use different, let's say, dimension to represent different infrastructures. And you will see later that we did use real number to represent electricity, and we use complex number, imaginary numbers, to represent ICT infrastructure. But when you have two different dimensions, real and imaginary parts, then when you do the eigenvalue analysis, you will find eigenvalues that are complex. But you want to be able still to rank with the same metrics nodes that are in the electric world with nodes that are in the communication world. That's why we need to play with what I call Hermitian matrix. And these Hermitian matrix helps to represent both physics and represent, you will see later, the bidirectional flows of information. Hermitian matrix is interesting because the transpose of an Hermitian matrix is the same. Why it is interesting? Because, again, when I will apply spectral analysis, eigenvalues, eigenvector, I will have the ability to have all the eigenvalues that are real, and I can compare them. So that's why I'm using Hermitian matrix. Eigensystems is the spectrum of the matrix, or I will call it eigenspectrum. And when you are using Hermitian matrix, all the eigenvalues are real values. That's very important. And I will define as the, let's say, the most important nodes, the largest eigenvalue and its corresponding largest eigenvectors to quantify the centrality, or if not centrality, criticity of each node in the interconnected system. So let's take an example, because I'm using a lot of words. Let's take a very simple graph. Okay, I have 6 nodes. First node is sending to a second node, that is sending to third node. Then we have bidirectional interaction between 3 and 6 and 2 and 5. And we have feedback from 6 to 5 and 5 to 4. You will see that this will be the basis of a simple power system later. If you do a representation of an adjacency matrix, representing only the directed problem, so depending on the if I'm going in or out in the complex dimension, real and imaginary part, this is something you are creating an adjacency matrix that is not Hermitian. It's not an Hermitian matrix. So what we are doing, we are using a rotation so that from this adjacency matrix that is representing something directed and not directed, we can find back a Hermitian matrix. And as you can see, this Hermitian matrix is fully with the property I was presenting. And important is that the eigenvalues are all real. There are no more imaginary parts. So once I find the eigenvalue analysis of my matrix, in which I put a given rotation, I can see, okay, my highest value of my eigenvector with related to my, so eigenvalue related to my eigenvector, I find the highest value as well. That will help me to find what is the most central node of my network. we discussed with Stan that it will be difficult to do all the different tests in Socrative. So let's skip the second survey to save time for interaction and questions. But the second test was about why Hermitian matrix is important. So as I was discussing before, it is important because, and in the example I was giving to you, in case of directed graph, you have adjacency matrix that is not Hermitian. If not Hermitian, you will have eigenvalues that are not real. So you cannot rank one value compared to another if it's not all a real part, only real part. And that's why we are using Hermitian method. And so let's go step by step toward the world we are really thinking about and into the smart city world. Let's focus on this very simple power system in which you have a production plan, okay, connected toward the first node, node of a transmission network, and a second node. In between you have a line, and at this node you have some loads. At every node of the power system, you have remote terminal units that are taking some values, whatever value, voltage, current, flow of power, active and reactive, both. And so as you can see, the blue area is the electrical power system, whereas the green area is the ICT world. Okay, and I'm using, as we present before, the source node of the electrical system, and you have the load that is in node 3. So flow of power is E1, E2. Flow of power is as well E3 and E4. I'm feeding the RTU. I'm supplying the power to the different RTU, and I'm having communication flowing from the control center to the RTU, to some actuator I'm having in the first node, electrical node, and to other actuators I'm having at the load side. And at that time, I will change a little bit my representation using both real part and imaginary part. And I'm defining as type 1, fully real, every interaction that are using the world of the electricity. So electric to electric interaction is type 1. Communication to communication is type 2. And once I'm having electric to communication, so typically this supply of power E3 and E4, I'm using type 3. And I'm using type 4 whenever I'm having communication to electricity. So again, the fact that you are sending some command control to different devices, appliances, that can change the power flow, for instance. I will merge type 3 and type 4 into a representation in the adjacency matrix that is both I'm having real plus imaginary value. Whereas type 1, electric to electric, is purely real value, and type 2 is purely imaginary values. So it is for indirect graph, and when you are directing the graph, you can change, and we propose you to use real value for type 1 or type 3, electricity service, okay? Whereas you have type 2 or type 4, communication service, will be purely imaginary. So it's very important, and it gives you the advantage to differentiate split the different infrastructure. And you can represent direct or indirect graph with the different services that are offered by both infrastructures. So what is the methodology and what we are using as algorithm? So I'm at first building the graph. So every electrical buses, every routers or switch will be defined as nodes. It's node in an electric world, it's a node in a communication world. You have as well all the different lines, both power line and communication links that will be defined as arcs. And I'm creating, as I was discussing before, the adjacency matrix depending on the type of interdependency. Either the interdependency of the service is electrical or is communication. So it will be either a real part or imaginary part or both. Once you have that, then you need to use the rotation in the space to find Hermitian matrices. Once you are sure that you are playing with Hermitian matrices, you are calculating the eigensystems, eigenvalues, eigenvectors. You rank eigenvalues. You identify the larger eigenvalues one by one. So you can find only one, but it's not the only one that is important. All the first one are important. So larger eigenvalues and their corresponding eigenvectors. You rank eigenvectors according to the norm, and you're able to identify the most central nodes. And the methodology is clear, and we can jump into an example so that you can understand more what is the aim of this method. Before take back home information, please remember, you need, whenever you are willing to secure a critical infrastructure, that is power system, but can be a smart city, you need to be able to rank the criticality of the nodes. Wherever it's a directed graph or multiple infrastructure. So to rank it, you can use spectral analysis, eigenvalues, eigenvectors, that are very interesting to rank a topology, a graph. And whenever you have only 2 dimensions, so electricity and communication, Hermitian matrix, spirit of Hermitian matrix is interesting because it helps you to be able to rank the different eigenvalues because they are comparable, they are all real. Let's now jump to application, a test system, and some results we find a few years ago. And we are using a distribution network that is, in fact, the outcome of a European project called Integral. So this distribution network, in fact, is a real network in France that we extract from a EDF database. We keep the same ratio for the lines, so to get the same voltage drops. We keep the same location of the different remotely controlled switches. At first, it was created to be able to represent a self-healing network. And the idea was, of course, it's in a lab, so not to have 30 megawatts of power in the lab, but the ratio on the power is 1000, and the ratio on the voltage is 150. So instead of 20 kilovolts, it's 400 volts. Instead of 30 MVA, it's 30 kVA. But we have real motors, real generators for the loads. We have transformers that are representing the primary substations. We have breakers, we have impedance, and resistant that are representing either underground cables or overhead lines. So it's a, let's say it's a real network that we have in the lab. In addition to this real network, even at reduced scale, we did implement in a French project a real SCADA system. So it's a SCADA system that is developed by Atos World Grid. Atos is using links for distribution network. So this is typically the SCADA system colleagues from Geneva in Switzerland are using. And thanks to a school of ICT, we did develop a, let's say, a communication network emulation. So having a real life behavior of the communication network, but everything that was emulated in a server, able to represent and to have the real software of Cisco switches or router, that will route the different data packets as it is in the real world with this scale of distribution network. We built as well some primary substation control with full 61 and 850 abilities, with both protection relays, control of the transformer, and the control of the different automation system inside. So the test system is 3 substations. In dark black, you have the electrical network. In red, this is a normally open lines. In solid black is the line that are normally closed. In blue, you have the communication network. In the communication network, we have 2 routers, 1 WiMAX, 8 multiplexer, 26 links, private LAN, Giga Ethernet, connecting, let's say, the core network of the telco communication company. Whereas the power system is at reduced scale, and we aggregate the different loads. So we are representing only 14 nodes with 17 lines. It is including 7 distributed generations, 9 loads, and 3 substations. This network can be represented as a graph that is presented here, with electric flow, with ICT flow, the supply of ICT network from some node in the power system, and the measurements we are having. And again, we did develop this network to be able to self-heal the network. So it is including really the complexity of a classical power system. At first, we can separate electrical layer and ICT layer, working with them completely differently. And so when you apply spectral analysis for the electric layer and for the communication layer, you will find the most important nodes in the power system and in the communication infrastructure. When you are using the coupled infrastructure, so having both of them represented, not only electrical by itself, and communication by itself, but with all the supply and data flow between the different infrastructure, you are ranking again node 1, 2, 20, and this time 22, that are nodes inside the network. Maybe it's more easy to represent it in a graph and in a matrix. So again, you remember, you have the power system world coupled with the communication network world. that is creating a graph that is in blue all the communication system. So again, I'm using imaginary values for the agency matrix. The solid dark, the wave is purely real. It is the electrical system. And all the red arcs are representing either supply to the RTU, but as well the RTU is sensing, is measuring things in the power system. And what is very interesting and what is surprising compared to all the risk analysis experts you have in the world working either in electrical field and in communication field is that those experts are able to rank the criticity of the node in the electrical world. So from 0 to 30 is the representation of the electrical world. And you can see that some nodes are more important than others. And this is the same for communication world that we have here. And what we were able to create, and that was not existing before, is the fact that at the far end of a power system where you have one RTU supplied, for an expert of risk analysis, okay, you lose one electrical node, you don't care, it's one node. But the issue is that if this node is in fact responsible for the supply of a RTU, and this RTU is responsible of some automation function in a smart grid, you're screwed, it will not work anymore. And so we were able to find what was the most critical links between power system world and communication world. So that was the results, and I'm almost on time. I will jump now into okay. Let's take few minutes. Oh, yeah. Let's take a few minutes to do a second Socrative test so that you can answer. So I will close this activity. I hope it was saved, just because it seems that I had an issue with the connection. I will launch a second quiz. And again, I'm kindly asking you to jump into Socrative, use the room Caire 1, 2, 4, 3, as you did before. I'm doing it as well. And this is just a way for me to get from you if you have other ideas about how we could assess interactions between the different infrastructures. So please feel free to add any type of other methods you already experiment yourself, just to let me know what things we may miss during the thesis or during the different projects we were running on the critical infrastructure protection. Okay, so we already discussed about betweenness centrality. Let's jump on the take back home information. So please remember that studying at least two infrastructure together, being able to separate their services into two different worlds. So it's already complicated to solve. And what we did propose is one way to solve risk analysis for complex and interdependent infrastructures, which usually are studies by different experts. And as I present you, this is a way to find some critical interdependence, and typically the ones you need to secure at first to be able to have the more resilient system of system or smart energy system. So if I jump now into the conclusion and further work before the evaluation of this presentation. So let me summarize what we discussed today. So there is really a need of original and innovative methodologies to be able to study the interdependencies and the vulnerabilities of interconnected systems. I was presenting you, but it's not the only one, complex networks, which is promising to study the topological weaknesses of large interconnected systems. The proposition is flexible, and you will see in further work how we can extend it. It's flexible and should be able to be used to study other infrastructure different to ICT and power systems, but you can add, for sure, can add gas, water, recycling, we discussed already, and so on. And I was pushing toward you the use of emission matrix and eigenspectral analysis to study the structure of coupled infrastructures. So further work, where are we going? Of course, we need to validate the models. And so at first, to validate topological approach, we can think about combined simulator. So having simulators able to discuss with FMU, FMI, for instance, process, make sure that what we are assessing as most critical nodes are with a simulation approach indeed very important. We can, of course, rely on what we create in Predis, so reduced scale networks in which you have representation of both power system and communication. Is a Predis center that is hosted in my lab, in my school. We want to incorporate dynamic aspects. So dynamic not as oscillation that the colleagues from control system are doing, but other type of dynamic aspects. As I have a power system problem that will lead to a blackout, all these different trajectories can happen. So dynamic aspects, the same as we are typically analyzing in a pandemia situation, as the COVID we are now having. We need to have cross-disciplinary approach, of course. And so we need to incorporate people from control system, markets, human behavior, to have this extended towards smart cities. We can extend the modeling based on smart grid architecture modeling. This smart grid architecture modeling is proposing different layers, so three-dimension way of just studying electrical components and ICT components, but you can as well extend this to multi-infrastructure. And so there is a real potential in this area of research. So my my presentation is over. I hope I'm almost on time. I'm asking you to jump to a last test on Socrative. So I will close. I don't have that much answer for the second test, but okay, let's sorry about that. I will close this one. You will be able to send me information by email. I'm proposing you to evaluate what I did. And so this is typical question that usually you are feeling after every courses. Was my level of voice was okay, and the different support was okay as well. So please fill it. It's a good way for me to be able to enhance this type of presentation. And so this is a survey you can fill later. I hope it will not be disconnected again. I don't know what Socrative is experiencing as problem. But so last survey is about the evaluation of this lecture. And I don't know exactly, Stan, maybe you can explain how we can interact, if it's through the chat or through yourself, if there are any questions about my presentation.
Yes, Raphael, thank you for your presentation. Well, actually, the majority of the questions, all of the questions are going through the chat of YouTube channel. And well, it's my duty to provide you all of the questions from the chat. Well, actually, at the moment, we have about 10 questions. And first of all, I just have one of the questions to you. It's a sort of some of the organizational questions, but it was put by the organization committee of today's visionary lecture. And the question is, will it be possible to distribute the presentation, maybe in PDF form, for the online participants of today's listeners of today's visionary lecture?
Yes, of course, no problem. No problem.
Okay, that's great. So, and well, if you do not mind, we'll pass to the question and answer section of our today's lecture. And the first question comes from Ryazantsev Nikita. The question is, why is government so important if it planned emergency activities right, so it's no need to supply it?
Yeah, so hidden behind government, in fact, you need to put all the different services belonging to it. So, for instance, police and firemen and so on. This is typically what we hide behind government. So, indeed, you could say, okay, we don't care about politicians. But in fact, it's not what is hidden behind government is not politician. Is all the services that belong to the government for the let's say coordination. And of course, if you're not able to feed a police station or fire station, it will be really a problem for them to be able to react facing blackout or other type of situations.
Thank you, Raphael. And the second question goes from Dmitry Pelegov. And could you please estimate the possible change of direct current alternating current balance in future smart grids due to increasing role of renewable energy sources, electromobiles, and large battery energy storage systems?
So it's a little bit aside from my presentation of today, but indeed HVDC is impacting a lot our smart grid, let's say, and power system balance and equilibrium. If this question, if my answer 10 years ago would have been completely different, and for sure things are moving very fast. So I know that, for instance, colleagues in Singapore, and it's the same in France, they are starting to issue some devices that will be either completely included in the secondary substations, static transformer, or adding devices aside, just to make sure that in secondary substation, you have, of course, your three-phase distribution system that is available, but you have as well a DC link that is available to supply, to feed charging infrastructure, battery infrastructure, and if possible, as well, renewable infrastructure that is producing power directly in DC current. So if you start with this assumption that the utilities are ready to change the distribution network architecture, so to implement more and more DC, it will change a lot, because if it's only local, as I was describing, at the level of LV network, it will allow to have much more efficient local energy communities that will share with this DC link more easily the resources that are renewables, storage units, either static, I mean batteries that you are putting on the wall board, Tesla battery, but as well storage that is moving, so electric vehicle having the vehicle to grid ability. So it will change a lot at first those local areas. It will change the power system world at transmission level, but we know it already. It's HVDC links one by one or multiple ones that allow to go through very large areas, very long distance, and are able to damp oscillation, but not able to provide short circuit current. So it is changing a little bit power system viewpoint. But is missing when I'm describing this. You see, I'm describing LV, I'm describing HV, and is missing somehow infrastructure in between. So for sure, because of some economical, technical balances, we will still build HVDC lines, interconnecting, for instance, renewable offshore. We will jump more and more into studies implementing DC at low voltage level. But for a system world with the AC, NC, and Volta viewpoint, will still be there for a few years. We will not do the revolution, and anyway, the cost of jumping to AC to DC is too high. The standards are there in place, so it will not move that quickly. But what can move very quickly is indeed local DC systems and HVDC that will interconnect more and more renewables offshore, more especially, but that will give more and more issue about stability of power systems. Okay, it helps for damping oscillation, but it cannot help for a loss of synchronizing torque and loss of short-circuit current.
Thank you, Raphael. And now the third question comes from Alexandra Halisma. And to my point of view, it's quite philosophical question. And digital technologies provide opportunities in terms of control, reliability, etc. But simultaneously, we are pushing ourselves towards the new threats of ICT terrorism. So is there any optimal balance between digital and non-digital technologies in the industry?
Yeah. So thanks a lot to Alexandra for this question, because this is completely what I wanted to push in this presentation. If we are pushing more and more digital approach, we call now the 4D revolution. The world will be more digitalized, decarbonized, decentralized, and democratized. In fact, more digital is indeed increasing the risk of cyber threats. Cyber with any type of problems. So it can be someone is in his room trying to hack something, but it can be government trying to attack other countries. Anyway, having all our systems, smart cities, relying on a coordination with and something that is purely digital is, for me, very dangerous. And this is why we need to push forward what I was presenting today. Can we study? Can we do the proper risk analysis so that we are able to rank at which level we need to secure, we need to reinforce our systems, making sure that there are no new threats appearing with this cyber issue and the fact that digital will rule everything. Because indeed, when you're able to shut down a power system remotely from your garage or your cave, it is starting to be dangerous, but it's typically what can happen already today, and what already happened in the past. So yes, dangerous. Still, in fact, the conversion toward the previous world of control to the digital world is already occurring, and we cannot change it. I mean, we cannot say we want to go back to a relay type of control because of the saving digital was able to implement in the various industries. I'm sure your Alexandra is not ready to say, okay, I will not rent any taxi through the phone, as it was the case 20 years ago. I prefer to use Yandef or whatever is the app she's using. It's so easy now, thanks to those tools, that now you are forgetting slowly by slowly what we did before. And even what we did before by the phone was line commuted 30 years ago. It's not the case anymore now. Everything is IP. The discussion we are having now, of course, obviously is IP based, but all the communication infrastructure, phone, is IP based. So we already put the finger in this trend, and it's almost impossible to go back. So we need now to think about cyber threats cautiously, and so to make sure that the system of systems we will create are not weaker than the one we had before.
Thank you, Raphael. Well, actually, the next question goes from me personally, and I was just wondering about the model of coupled infrastructures you were presenting, and well, before you showed the slide. Putting the question of what other infrastructures could be coupled. Actually, I've provided this question to the slide, and my question is, so from your point of view, what other infrastructures could be coupled in the model? For example, like economy, energy markets, or some, I don't know, like ecology infrastructures and some external influences. Lots of different things to be taken into account.
Yes. So we need to be careful about jumping into too much complexity too quickly, because at first we need to be able to validate at least on an infrastructure that is coherent and where we are sure that our model is giving the correct answer. So I think that the best strategy will be to go step by step and adding one additional infrastructure and one other. And that's why I was pushing forward the smart city question at first. I think that the next one we need to implement is the electric mobility, because of the obvious link we have with the electrical infrastructure and the obvious link we have with the ICT infrastructure. And then we can go further. Depending on the smart city we are thinking about, we might use gas as the next one, because more and more people are thinking about power to gas infrastructures, so that you're able to, whenever you have too much electricity, you're able to do some methanization or CHP, so to build some gas and to put in a infrastructure that is a little bit different, but that is offering more storage ability. So it's typically the next one. So again, we need to add step by step. But when we discuss about people from smart cities, in fact, clearly they want all of them now. And you know why they want all of them now? It's just because they are not mastering anything more. They put some apps because of some large supplier saying, okay, no, please go into full digital, it's great, use cloud, use blah, blah, blah. And in fact, the people from smart cities are starting to be very afraid, because they did create a very complex system of systems. They don't understand anymore. They don't have any expert able to tell them this is interdependent with this. And when something is failing, no one is able to restart it. It's not as in Windows, you go and you can put restart. It's not that easy. And so as researcher, we want to be cautious and go step by step. As a governmental person or as smart city rulers, they want to have everything, but they need it, in fact, urgently.
Yeah, thank you, Raphael. And well, actually, we do not have too much time left, but anyway, I think there is a time for a couple of questions. But if you do not mind, the rest of the questions I'll send you by email. Yes, so if you find some time, maybe we'd be really glad to see your answers. Yes, and the listeners would be really pleased for this. And just a couple of questions, maybe dealing with the methodology itself. Yes, and the question goes from Alexei Pardanov. Dear Professor, I did not understand how to create the graph for further conversions and how to evaluate physical and information amounts on graph branches. And could you please explain this?
So be careful, because I'm representing only topological links at first. Of course, you can use the graph to represent the flow of information. But when you are starting to do this, the arc are concentrating two informations, the flow and the topology. And I was interested, as I was explaining before, to go step by step. I was interested to do a step-by-step approach and not jumping too quickly into this very complex part. In fact, we tried, but that's why I'm explaining you that we need to be cautious. If you jump too quickly into the level of use of the different infrastructure with the flow, it's starting to be complicated. Still, complex network theory offer very nice tools for that. And one of the tools I was presenting is completely fitted. It is the betweenness centrality. Betweenness centrality is concentrating all the shortest path. So it will represent very easily the ICT load. So only in the ICT infrastructure, it will be quite correct. In the power system, the problem is that betweenness centrality is absolutely not representing the Kirchhoff laws. If you want to represent Kirchhoff laws, well, you need a load flow because a load flow can be represented with spectral approaches, but it's a little bit complicated. So I have some colleagues in Grenoble that did start to do some spectral analysis with graph implementing load flow, but it's very quickly something that are complicated and that are not fitted with the spirit of graph theory that should implement only easy and linear process for the analysis.
Thank you, Raphael. And well, actually, I think the next question, which comes from John Winner, deals with linearity and non-linearity. And John says that our world is highly non-linear, and most linear approaches describe only local stability, local extremum, and but not the global one, because in the real case we have multiple extremum cases. And he asks, what about non-linear approach for this case study?
So we have to consider what type of non-linearity is interested in. So again, because we did test a lot of different other methods that are more suitable for non-linear approaches, but that are less trustable with the result they are able to give. We at first jump into the topological approach. So topological is interesting because, again, this is something that is clear. There is no non-linear behavior of a link. There is a link between A and B. And that's why we limit, I did limit myself in this lecture to this specific case. But I fully understand that is willing to go further, and in that case, complex network theory can be used, and for sure you can discuss with colleagues from control guys that are using some approaches, linear approaches, quadratic approaches with the graph. But it's very quickly become something that is complicated, and the trustability is not that easy. So I think that most probably we need to couple tools, because there are tools that are very strong to do one thing, but pushing one tool into something where is not fitted for is dangerous. So this is typically something you need then to say, okay, let's couple Markov or agent-based multi-agent simulation with topological approach to be able to see both at the same time. Let me try to take, if I have time, I can maybe give you directly to the chat the link to my presentation so that the colleagues will be able to download it. But at the same time, I can maybe answer to the next question.
Yes, thank you, Raphael. Well, actually, we are almost completely out of time, but I think we have the time for the last question. I think that the last question would be a sort of the light one, yes, and it's like it comes from Vladimir Grenoble. And dear Professor Raphael, are you willing to create and develop a new course for digital university together in collaboration with Ural Federal University?
Well, maybe you need to, Stan, you need to broadcast the information with Essence, but that's for sure. Essence project is a EU project and is fitted for the let's say more interaction between some universities in Europe and in Russia and in Vietnam, and this is really typically what we want to create. That's for sure. Is it a course, or is it something that is? So I'm copying it. Is it a course, or is it other way to interact? So with you and Alexandra, we did try to create a combined research project. So from my experience, building some strong links between universities usually is starting from strong research collaboration before discussing with let's say education. So once we are able to have some first results at research level, usually we are able to create more links for the students themselves. I mean, undergrad and grad. So I think that it's a very good idea, and we need to work further, either in the framework of Essence project or in the other projects we'll be able to create together.
Thank you very much, Raphael. Actually, if you do not mind, I'll take the concluding remarks, yes, of today's visionary lecture. And firstly, I beg for pardon for all of the participants whose questions were not addressed within online session, but I take my personal responsibility on distributing all of your questions and sending these questions to Raphael. And I hope, I suppose you'll get the answers. And thank you very much for being with us today. Raphael, thank you very much for taking your time and providing that very interesting visionary lecture. And I hope, it will be not the last time, yes, with us. And thank you very much. Well, that's all for today. Thank you.
Thanks a lot, Stan. Thanks a lot, Alexandra, and hope to have the opportunity to discuss again either in Russia or remotely. So the presentation of today was either these interdependencies, and I will be able as well to take some time to discuss with you about a EU project I was coordinating a few years ago that is in the framework of ICT and distributed, let's say, intelligence into the grid. Anyway, thanks again for the invitation, and hope to see you or discuss with you later. Bye.
Thank you very much, Raphael. It was our greatest pleasure. Thank you. Bye.
Bye.